Good morning, folks. Today we are talking about Chapter 2 of Logic and Contemporary Rhetoric. It's in some ways a continuation of the first chapter. This one's a little bit more on deduction and induction. We're going to be seeing more specific examples of deduction and inductive reasoning in action. We're going to see some valid patterns as well as some invalid patterns. And we are going to be briefly introduced to something called propositional logic at the beginning of the chapter. And that's part of what I will be talking about today. Now, this is an overview course. It's kind of a survey of logic, so admittedly, we can't cover as much of the ground as I would like to cover. However, I will likely cover a good bit more ground than is actually in the textbook about this to hopefully get us a decent understanding. Now, the first examples when fleshing out this, this explanation of deduction are examples from something called propositional logic. These methods of propositional logic began to be developed in the 19th century and into the 20th century. The older kind of deductive logic that started with the Greeks and was the dominant form of deduction all the way up through the 19th century is called categorical logic. Has anyone heard of so-called categorical syllogisms? Has anyone done syllogisms in a math class or somewhere? Yeah, there's some crossover here. Well, we're going to be looking at categorical syllogisms more in some upcoming lectures. I wanted to talk now about some basics of propositional logic. Now, the main reason why we call it propositional logic is because the main unit of discourse are statements or propositions. Now, that example that I've already shown you, modus ponens, is one of the most basic structures of propositional logic. There are two propositions followed by a conclusion. If it's the case that A, then it's the case that B. And by the way, you might see me write it this way. This is actually the one preferred by logicians. Some textbooks simply write it this way. This statement is an if-then statement. We call them conditionals. I've said this before, but I'll say it again. They are called conditionals because what we are saying is, if it's the case that this side of the conditional is true, then this one will also be the case. Now, just to give you a little bit of language that is implicitly in the textbook, but the author doesn't clearly define, in my opinion, a conditional will include two parts. This front end we call the antecedent, and this tail end we call the consequent. If A, then B. Now, the second proposition in modus ponens is, well, it's the case that A. Therefore, what follows? B. If the connection is a good one, then the light bulb will go off, or will go on, excuse me. The connection is a good one. Therefore, the light bulb will go on. If this animal is a wallaby, then it's a marsupial. The animal is a wallaby. Therefore, it's a marsupial. If it's raining, then the plants will be sufficiently fed. It's raining, ergo the plants will be sufficiently fed. Now, the reason why this is a deductively valid structure is because we had said that if this is the case with the conditional, then the consequent follows. What we did right here is we affirmed the antecedent. That's what modus ponens roughly means, translated into plain English. If A then B, we affirmed A, B is the case. Now keep in mind, this is a valid structure. If you put garbage into it, that is false premises, then the argument is unsound, regardless of whether or not the conclusion is true or not. Next. Modus tollens. Modus tollens runs such. If it's the case that A, then it's the case that B. But the second premise says it's not the case that B. Now, I said this once before, and I'll say it again. This tilde symbol that is on your computer keyboard is the symbol that logicians use for the word not, or not the case. Now, folks, you might like to ask, and I'll say it if you're interested, you might ask, why go through all this? Why take real-life language and translate it into this symbol language? Well, there were some thinkers who believed, and I think rightly so, that if we could take all arguments and boil them down to their basic structure, we would understand the arguments better, and we would actually be in a better position to evaluate them. Because language is often confusing and muddy. So if we could boil down the argument to its fundamental structure, we can more easily tell if it's valid or invalid. Now, indeed, it's a little bit of new stuff to get used to. But yeah, once we boil things down into their basic structures, they're actually easier to evaluate. Oh, I didn't finish. The conclusion to this argument is, therefore, not A. If the wire is made of copper, then it will conduct electricity. This wire doesn't conduct electricity. Therefore, it must not be made of copper. If this animal is a wallaby, then it's a marsupial. But this animal is not a marsupial. Therefore, it can't be a wallaby. Now, for those of you who like diagrams, shudder. I know some people shudder at diagrams. Some of us like diagrams because I'm a little dense, and sometimes I need to visually see the relationships in order to make sense of them. It's not magic that goes on in my head. I can't just see whether something's deductively valid or not just by reading it. So sometimes tools can help me to see things better. Let's get back to our marsupials and wallabies. Suppose that this circle right here represents the class of all things marsupial. Guess where I'm going to put my wallabies? Inside of that circle, because wallabies are a what? Yeah, we call it a subset of the larger set of all things marsupial. Don't worry, this is as mathsy as it gets. Now take a guess what is outside the circle of all things marsupial. Everything outside is non-marsupial. Now, I'm comfortable with this stuff because it's perfectly binary. It is the case or it isn't the case. Now, you'll notice if I say, if it's a wallaby, then it's a marsupial. But I said, but it's not a marsupial. So it would be somewhere out here. And if it's somewhere out here, it sure as Hades can't be this. Yeah, Simeon.
Yeah, so if you were to switch the antecedent and the consequent, it would no longer be valid?
Yes. And perfect time to mention this. There are two propositional logic deductively invalid structures that the author introduces at this point in order to illustrate. I'm actually going to show you both of them. This first one is called affirming the consequent. And unsurprisingly, guess what the second premise does? It affirms the consequent. It looks like this. If A, then B. The second premise says it's the case that B. And then it tries to draw the conclusion A. Guess what? This is an invalid form. Why? Because the conditional relationship only goes what? It's a one-way directional. All it's saying is if it's this, then it's this. Then this is the case. It's not saying if this, then this. If it's a wallaby, then it's a marsupial. This animal is indeed a marsupial. Well, guess what? We can't conclude just because it's a marsupial that it's a wallaby. Well, why? Because there's a lot of other, marsupials that are not wallabies. Just like we could say, if this wire is made of copper, it will conduct electricity. Well, this wire here conducts electricity. Can we be sure that it's copper? The answer is no, because there's lots of things that conduct electricity, including human bodies. Now, this next one, I could have left the word invalid up here, is called denying the antecedent. It starts with a conditional again. If it's the case that A, it's the case that B. Now the second premise says, but it's not the case that A. And then it tries to draw the conclusion, therefore not B. This is an invalid form called denying the antecedent. And again, mechanically speaking, the reason why this one is invalid is because of the one-way direction of the inference. Now you'll notice that this looks a little bit like what? It looks a little bit like the reverse of modus tollens. Now let's run through an example. If this is a marsupial, then it's, if this is a wallaby, then it's a marsupial. But it's not a wallaby. Can I therefore conclude that it's not a marsupial? No, for the same reason I said before, because there's a lot of things that are marsupials but are not wallabies. Now, folks, the complicated reason why modus ponens and modus tollens are valid, but denying the antecedent and affirming the consequent are invalid, is because of the distinction between what are rightly called sufficient conditions and necessary conditions. Now you'll notice that this being the case is a sufficient condition for this being the case, but it's not a necessary condition. Now this necessarily following, or I said this being the case, is necessary to this. In other words, if it's indeed copper wire, it will be something that conducts electricity. You can't have one of these being the case, but the other not being the case. And really, all these are doing is fleshing out the logical connections between the two things that we're talking about here. And I don't want to be too flippant about this, but all that logic really does is it susses out the relationships between, or I should say, among concepts. It's really just articulating the relationships among concepts. Now, two more things really quickly with a little bit of time that I have. Now, these next two are deductively valid. And this one shouldn't really be any surprise to you. Oh, wow. The hypothetical syllogism ought to be rather straightforward. And by the way, folks, this word syllogism really isn't so fancy, Dan. It's really just a phrase for any argument that contains three statements. Two of them are premises, one is the conclusion. There's a lot of different kinds of syllogisms. Now, the hypothetical syllogism has two propositions. They are both conditionals. If it's the case that A, then it's the case that B. Two, if it's the case that B, then it's the case that C. Therefore, if it's the case that A, it's the case that C. If I buy these wonderful chips, then I'll eat the whole bag. If I eat the whole bag, then I'll be sure to get sick. Therefore, if I buy this wonderful bag of chips, then I'll be sure to get sick. Guess what? This looks like a homework exercise that you may have seen last time. A hypothetical syllogism was a piece of that argument. If it's a wallaby, then it's a marsupial. And if it's a marsupial, then it's a mammal. Therefore, if it's a marsupial, therefore it's a mammal. Now you'll notice that all the examples I gave here have been with true premises. And the conclusions followed by necessity. Now the last one. And then we'll have to call it a day. It's called the disjunctive syllogism. Now, folks, a disjunct is a phrase that is used for an either-or statement. Now, the reason that we call it a disjunct is because if an or statement is true, at least one of those sides of the or has got to be what? Not necessarily true. At least one's got to be true. This little symbol right here, this is the symbol that logicians use to mean or. The first proposition is, it is the case that P or it's the case that Q. The second premise says, but it's not the case that P. Well, guess what follows? Therefore, it must be Q. It's P or Q. Second premise is, but it's not P. Q follows by logical necessity. And by the way, this shouldn't be astounding because it's a very basic thing that logically follows. A little more on this next time, and then we'll get started with categorical syllogisms. Bye.